All right, so first up today, you are adding chain rule into your notes. You'll notice here what chain rule actually lets us work with and what it's oriented for. So it's talking about the derivative of f of g of x. So in other words, if we have a composition of functions, we're going to have to use chain rule. Or even as you're going to see most commonly, if you just have a function that doesn't just have a plain old x inside of it, we're going to have to use chain rule. And so notice what we end up doing is we end up doing the derivative of f with g of x still in it times the derivative of g of x. A way to remember it that maybe makes a little bit more sense just in terms of more real words that we would use on a day-in, day-out basis is down here. That basically means you do the derivative of the outer function times the derivative of the inner function. All right, so we're going to start by taking a look at some examples. And as we go through this, we're going to see some examples where we don't need chain rule and some where we do, just to be able to contrast those. And so it's a good idea that as we go through these, write them down, as well as the process that we go through in terms of actually getting answers out of them. Now notice the difference between these two equations. Why is one no chain rule and why is one with chain rule? Well, you notice that this first one, the b to the x on the left side here, is just x to the power of fifth. The power of 5 is like our function, but since I just have an x on the inside, I know how to deal with it. I can use power rule. However, over here, it's still being raised to the power of 5, but it's no longer just an x to the fifth. It's actually going to be this whole function, this polynomial, raised to the fifth. So basically, it's kind of like having a polynomial within a polynomial. All right, now, of course, we might as well take the low-hanging fruit since it's there. The one on the left there, the derivative of b of x, b prime of x, of course, that would be 5 times x to the fourth. But now for this chain rule side over here, when I go to find w prime of x, I'm going to have to do a little bit more work than that. So remember, our rule is that we do the derivative of the outer times the derivative of the inner. Well, the derivative of the outer here is the fifth power part. So that means, I already know what that is. That's 5 times something to the fourth, but it's no longer x to the fourth. It is the whole inner function in the place there. So it's 3x to the fourth plus 2x. That's all being raised to the fourth. So when we see that f of g of x, f prime of g of x, yeah, we do the derivative of f, meaning to the power of 5 like we normally would, but g is still plugged into it. All right, and now I'm going to multiply that by the derivative of the inner. So that means the derivative of 3x to the fourth plus 2x. So that's going to give me 12x cubed plus 2. That then is now your derivative. It allows us to find a derivative that we previously would have been unable to actually deal with. Now, this is fine as your final answer here, but I do want to show you how I would like it maybe simplified, cleaned up just a little bit. There's not a ton we need to do here because I don't expect you to actually put that out to the fourth power. But the 5 and the polynomial over here, I'm going to go ahead and multiply that 5 in there just because I think it looks a little cleaner. So I'm going to leave the 3x to the fourth plus 2x to the fourth. Nothing to do with that. I mean, we could multiply it out, but as you know, that's going to get really big, really ugly, so we aren't going to worry about it. But I am going to multiply the 5 into the other parentheses, so that gives me 60x cubed plus 10. Do you need to? No. It just maybe makes it a little bit cleaner. It gives us less pieces to this equation and to this expression that we actually have to worry about along the way. All right, now next up, we're going to see the many different iterations we've seen already for how to find the derivative of a function that looks like this. So write this equation down and make sure to write it down nice and neatly because we're going to come back to the same equation actually a couple times in a row here. For this first problem, what I'd like you to do, please, is multiply that out. So you know, actually do the 2x plus 1 times the 2x plus 1, multiply it out, write it in standard form. And then please find the derivative using power rule. All right, so first thing we need to do is go ahead and multiply this out. So I'm now dealing still just with f of x. And f of x, that means I'm going to be doing 2x plus 1 times 2x plus 1 and multiply everything in the first parentheses by everything in the second parentheses. And you should end up with 4x squared plus 4x plus 1. Now, that was what we were asked to do when we were told to multiply it out. Now we need to find out what f prime of x is. So f prime of x then is going to equal, by the power rule, 8x plus 4. All right, now we're going to repeat finding the derivative of the same equation, because we're wanting to actually see if this stuff all works out the way we think it should. But this time we're going to use the product rule. So if we're squaring it, we're multiplying it by itself. So find the product of those two. All right, so if we're going to use product rule here, for f prime of x then, I'm going to do the derivative of the first function. So derivative of 2x plus 1 is going to give me just 2. And then I multiply that by the second function exactly as it was. So 2x plus 1 stays the 2x plus 1. All right, and then that's going to be plus. And now we flip-flop which one we're taking the derivative of. And so the 2x plus 1 that we started with is as it was. And then we take the derivative of the second function, which is 2. And now, just to prove that these things all give us the same answers, let's go ahead and multiply this out and simplify it. So I distribute in that first 2, gives me 4x plus 1, plus distribute in this 2, gives me 4x plus 1. Go ahead and combine your like terms here, and f prime of x, you should find that it equals 8x plus, wait, something's wrong. What happened? Ah, yes. I didn't multiply the 2 into those, did I? Into the 1s. That should be a plus 2 and a plus 2. And so then, that's why it's yes plus 4. Notice one advantage of being able to do this by multiple methods is that you can check yourself that way. All right, so now next up, let's use our new chain rule and see that we can get the same thing out of it using that. All right, so as you're doing it again, remember with chain rule, you got to think about the function within the function. In this case, your inner function is going to be that 2x plus 1. Your outer function is the squared. The outer function is kind of like an x squared there. So we start by doing the derivative of the outer function. So the derivative of like an x squared would be 2x. So it's going to be 2 times, but the inner function is still stuck inside of it. It's not 2x, it's 2 times 2x plus 1. So that's derivative of the outer. And now we do it times the derivative of the inner. And the derivative of the inner, derivative of 2x plus 1 is just 2. All right, so there is our basic version. But yes, I definitely want to clean this up. I would want to clean it up whether we were trying to match it with the other ones or not. And so I got 2 2's outside. I can go ahead and multiply those first. So that means I'm distributing a 4 into the parentheses, which gives me 8x plus 4. Final answer, and it is in fact the same as what we got on the last 2 problems. So that's a relief that we're actually getting the same thing. We don't need to question everything in our lives this morning. Yay! All right, so now we're going to find the derivative of this function. So in this problem, I mean, we actually technically do have a couple different options about how we could approach it. We could use chain rule, but we also do have the option of actually multiplying it out. But this is a great example about why we probably don't want to multiply it out every time, right? And why we want to have something like chain rule. Because multiplying this out, bad, ugly, scary. Nope, don't want to go there. So we're going to use chain rule. And when using chain rule, think about what's the inner function, what's the outer function. The inner function here is this x cubed minus 1. So that's our inner function. And then our outer function is like x to the 100th. All right, and so when we go to find that derivative, we first do the derivative of the outer. So that's going to be the 100 times something to the 99th. In this case, that something is the original x cubed minus 1. And then I multiply that by the derivative of the inner function. So now that means I'm going to do the derivative of the x cubed minus 1. So that gives me 3x squared. And then once again, I look to see, can I actually clean that up at all? And to me, yes, I would say I do want to clean that up just a little bit. So g prime of x is going to equal certainly this x cubed minus 1 all to the 99th. I definitely am going to leave that way. I do not want to actually have to multiply that up. But I can actually multiply this 100 by the 3x squared. And since that's going to give me a monomial, I'm actually going to choose to write that first, because I always like to write my monomials first. So that's going to give me 300 x squared times that x cubed minus 1 to the 99th. All right, so now that we've practiced a few of these, I think you got the hang of it. Go ahead and find the derivative of each of these two functions, please, on your own. Okay, here you can check your final answer for the first part, h of x. And here's your final answer for r prime of x, the second part there. And yes, notice I did distribute that 100 into the second parentheses just to make things a little bit cleaner. It means I have less pieces to the equation to have to wrestle with, so it's always a good thing to clean it up that way if you can. Little side question related to that. Could I have distributed the 100 into this set of parentheses? And the answer ends up being no. Because that parentheses is to the power of 99, and the 100 is not to the power of 99. I could only distribute in like maybe the 99th root of 100 or something crazy like that. So, no. We cannot actually distribute that into it because of the exponent on it. So that's why I can distribute it into this one, because there's no exponent on that parentheses. All right, so now we're going to add in a layer into our chain rule work that we've been doing, because so far everything that we've done has just been polynomials. Now we're going to throw in some of our trig functions that we've been able to take the derivative of most recently. And so again, taking a look to see when do we and don't we need to use the chain rule. So first up, for this c of x equation over here, if I wanted to figure out what c prime was, I'd end up just doing 3 times the derivative of sine of x, because it's just an x that's inside of sine. When it's just plain old x, I just use the derivative rule I already know, which is that the derivative of sine is cosine. So that's going to be 3 times cosine of x. And that's the final answer, because of course, remember, when you multiply by a constant, the constant just multiplies by your derivative. Now for d of x, it's a different story though, because for d of x, notice it's not sine of x anymore. It's now sine of x squared. And because there's a function inside of my function, I'm going to have to use chain rule. All right, so to find d prime of x now, I start by doing derivative of the outer function. So that's going to be 3 times, the derivative of sine was cosine, but instead of cosine of x, it's cosine of whatever's inside there. So it's cosine of x squared. And then that gets multiplied by the derivative of the inner function. So that means the derivative of the x squared. Okay, so the derivative of x squared then is 2x. Now looking at my resulting equation, I ask myself, can I write that any more simply? Can I make this a little bit cleaner? It looks to me like I can. So I go d prime of x equals, because the parts that look like they can easily be cleaned up are those. I can put that 3 and the 2x together. And so if we do that, that gives me a 6x times cosine of x squared. It's still not super neat and clean, but it's certainly a little bit neater and cleaner than that last line was. So yes, I do need to do that. All right, so when we go to find the derivative of m of x, I'm going to do the derivative of the outer first. So that means I got to look back at my notes and see what's the derivative of secant. And I see that the derivative of secant is secant tangent. But it's not going to be secant x tangent x anymore, because it's always whatever that inner function is still inside there. So it's actually secant of 3x times tangent of 3x. And that's just the derivative of the outer, which still has to be multiplied by the derivative of the inner. And the derivative of 3x is just 3. Now, how can we clean it up? There's not a lot of cleanup that we can do, really. I mean, all I would do is just write that 3 first, and then just write it a little bit more neatly. Now we go on to the second one. We're again following the same kind of pattern. So to get p prime of x, I'm going to do the derivative of the outer, so that's derivative of tangent, which is secant squared. But remember, it's not secant squared of x, it's secant squared of the inner function, so it's of the cosine of x plus 5. So that's derivative of the outer part. Now we still have to multiply that by the derivative of the inner function. So that means the derivative of cosine of x plus 5. Well, the plus 5, of course, that ends up being 0 when we take the derivative. So it's just cosine of x that we're finding the derivative of, and that is negative sine of x. And then, yes, we could look into maybe cleaning that up a little bit, especially putting that negative out front. But rather than focusing now on some of that cleanup, I want to show you a different way of looking at this problem. It's not necessarily the way that you will definitely want to do it, but for some of you, it's going to be a preferred way to look at it. Because for some of us, this whole inner-outer thing can sometimes get a little confusing. We can lose track of which one is which and what really represents what, especially as these things get more and more complex. So there's a technique in calculus called U substitution, and basically that's what we're going to be taking a look at here, where I name the inner function as being u, the letter u. So in this case, u would have been cosine of x plus 5. Which means that rather than having to worry about this p of x thing, I can rather think of it as p of u. And p of u, instead of being that big ugly function, it's just tangent of u. And so the idea behind this technique is it lets you actually look at it in simpler pieces. You're basically breaking it down into its smaller functions. And so if I were using this technique, and again, you don't have to use it, but I want you to be aware of it, and a few of you might actually like it to where you would use it, I would find the derivative of each of those two functions. So u prime would be the negative sine of x, and p prime of u would be the derivative of tangent, which again is secant squared, but it's of u. I don't have to worry about keeping track of that whole cosine of x plus 5 thing sitting in there. And then chain rule says we multiply the two derivatives. So the derivative then would be p of x equals the negative sine x times the derivative of p that we found, which was secant squared of u. And then I could actually write u here, and then on the, actually I should do it that way. But I don't want to leave that u in there, so then I want it all to be in terms of x, so I go p of x equals negative sine x secant squared, and then I go ahead and just replace in what u was, which was the cosine of x plus 5. So it's just a different way of using chain rule. If you like that method, by all means, feel free to use it. In fact, if you like it, it can even help you later, because the use substitution comes up in other ways in calculus where you'll actually have to use it, but of course you don't have to use it till then. It's just a different way of looking at it, and another way of kind of understanding what's going on with this chain rule, because really what we're doing is we're breaking it into two separate functions and finding those individual derivatives. Then on to taking a look at these two problems now. Now these two are still going to end up being chain rule, but we really need to make sure we understand what we're doing with them, because sometimes the formatting of these particular functions can cause us problems. In the case of t of x, let's take a look at t of x first. What's the inner function? And so to see how to rewrite this function, which is what's really going to help us here, is really what I'm thinking is what's being raised to the power of 5? It's the sine of x. It's not sine to the 5th of x. What it's really meaning in this little shorthand that we've always used is it means that we're doing sine of x to the power of 5. And if I rewrite it that way first, it makes chain rule a whole lot easier, right? Because now you can see what's the inner function? Sine of x. Now you can go ahead and find your derivative using chain rule. All right, so for the t of x equation, I first do the derivative of the outer, and the outer here is something to the 5th. That's why I like the u substitution, because I can actually say it's u to the 5th. It gives me something concrete to talk about. But I do the derivative of that part first. So power rule, the 5 comes out front, and then I subtract 1 from the 5, and then the inside function stays the inside function there. And then I multiply that by the derivative of the inner function. So the derivative of sine is cosine, and that gives me my answer. And yes, that looks good, and that looks simplified, so we can go ahead and leave it just like that. And then we repeat the same process there for g of x. All right, and then once we have g prime of x, can we simplify that? Yeah, maybe a little bit. Sometimes that negative that's hanging out on the inside irritates me, and I just really have to pull it out and make it a negative 2 cosine sine instead. So far, we have applied chain rule here with polynomial functions, and now just with trig functions. Which type of function does that leave us that we've already worked with this year but haven't used today? How about exponential? Our e to the x equation, which was always interesting because that's the one where it is its own derivative. So we can start seeing what happens now when you start putting functions within it and how that might change some of its inherent simplicity. Because, of course, you know, if something's simple, we can always find a way to make it complicated in math. All right. So again, starting by taking a look at where do we and don't we need to use chain rule. So for our first one over here, n of x, of course, we're told up front that we do not need to use the chain rule here. Because in order to find n prime of x, the 10 out front is just a constant multiplied by it. So we know we're just going to multiply my derivative by that same constant. It's 10 times whatever. And then the derivative of e to the x, I actually know the derivative of e to the x is e to the x. Notice it's only an x in there. But the second function here, the m of x, notice it's not e to the x anymore. It's e to the tangent of x. And e to the tangent of x means we now have a function within a function going on here. So, in order to find m prime of x, we need to first figure out what's the inner and what's the outer function. And this is also a great example as well about where, for some of you at least, that u substitution can be a good way to look at it. Because if I'm looking at this function, it's normally e to whatever it is. But in this case, it's going to be e to the u, because I plugged something in where x normally lives. What would that make u? That would make u be tangent of x. That little mental exercise there tells me what the inner and outer is, because u is the inner. And then whatever I plug u into, that's the outer function. So it just helps me to keep track about which one's inner and which one's outer. So, going back to my problem here, to find the derivative, of course the 10 stays the 10. And then I'm going to do the derivative of the outer function. So that's the e to the power of something. So it's going to be its own derivative. So the derivative is e to the power of that same something. So it's e to the power of tangent of x. And then I'm going to multiply that by the derivative of the inner function, which is what goes in for u, if we're thinking of it in terms of u substitution, or in other words, where I used to just have an x, now I have a tangent of x. So what's the derivative of tangent of x? Secant squared x. So I go secant squared x, and there I have my answer for that one. There I can actually see using chain rule. For some people, when we get into the exponentials, chain rule can seem a little bit harder because our inner function is in the exponent, and it doesn't look inner there. It's not like we put parentheses around exponents or something like that, which is what we do with some of the polynomials and with the trigonometric functions. So it doesn't look as inner. In fact, it kind of looks like it's at the end. But we got to remember that whatever is normally the x, whatever's in that place, that is actually our inner function. All right, now we're going to see that in action a little bit more here. So here's a nice simple derivative. It doesn't look quite as odd as having to the power of tangent of x. We want to find the derivative of h of x here. All right, so in doing this one, I need to find the derivative, which means first doing the derivative of the outer function. That's the e to the power of something, so it's going to stay e to the power of the same thing. So that's e to the 5x. And now I'm going to multiply that by the derivative of the inner function. In this case, the inner function is the exponent, so that's the 5x. So the derivative of 5x is 5. Which means that my final answer then is going to be 5e to the 5x. And finally, I'd now like you to find the derivative of this function. M of x equals e to the sine of x. And why is e raised to the power of sine of x? Well, it's probably better not to ask. But it is going to give us some excellent practice in seeing how we deal with some ugly situations so that no matter what you end up facing in reality, you'll know the skills about how to handle it. All right, and so now I go ahead and use my chain rule, and I know I have to use chain rule because it's no longer e to the x, it's e to a function. So I do derivative of the outer, which is derivative of e to the whatever, so it stays e to the whatever. At least e to the power of something is easy when you find derivative. All right, and then I got to multiply that by the derivative of the inner function, which is derivative of sine. The derivative of sine is cosine. So this whole thing ends up being multiplied by cosine of x. And yeah, we can go ahead and leave it just like that.